Good day, everyone. Good day, Miss Catherine Borgonia, and good day to our classmates. We are Group 6, and we are going to present our report on topographic survey. So, a brief overview of what we are going to cover for this report. First would be the introduction, next would be contours, lastly, will be the checkerboard method. Introduction. A topographic survey is a systematic and detailed examination of the physical features of a piece of land or a geographic area. This survey aims to precisely measure and map the elevations, contours, and characteristics of the terrain. The resulting topographic map provides a visual representation of the land's surface, highlighting the varying heights, slopes, and any significant natural or man made features. Imagine a world without the ability to map our surroundings, assess landscapes, plan infrastructure, or even understand the impact of environmental changes. This world would lack the essential knowledge needed for sustainable development, risk management, and countless other crucial activities. Fortunately, topographic surveys provide us with the means to comprehend and navigate the intricacies of our natural and built environments. So, covered in topographic surveys are vertical data, which is elevation, height. These are the distinguishing characteristics of topographic maps. Topographic maps show the configuration or shape and roughness of the ground. This roughness is commonly referred to as relief. Throughout time, depiction of the relief of a parcel of land changes. Topographic surveys involve all procedures, equipment, and methods necessary to capture both horizontal and vertical data of points on the ground so strategically chosen to depict the terrain. Modern topographic maps represent points that have identical elevations with lines called contours. The elevation on these lines are based on known or assumed datum. So, what are the different kinds of topographic maps? Sugar loaves. A sugar loaf topographic map typically refers to a map that depicts the topography of a specific geographic feature known as a sugar loaf. A sugar loaf is a term used to describe a conical or near conical hill or mountain with a pointed sugar loaf like shape. These landforms are characterized by steep sides and a relatively smooth, rounded summit. A Sugarloaf topographic map would focus on providing detailed elevation, contour, and slope information for the specific Sugarloaf feature. This type of map helps hikers, climbers, geologists, and outdoor enthusiasts understand the terrain, elevation changes, and potential challenges associated with ascending or navigating around the Sugarloaf. These are idealized depictions from a side or oblique view. The only form of topography on early maps is found in the 17th century due to a lack of detailed surveying. So back at the 17th century, the Sugarloaves topographic maps was considered to be the only form of topography. The Sugarloaves topographic maps gives locations of mountains, hills, but not the precise size. So, what are its advantages? Detailed terrain information. These maps provide detailed information about the elevation, contours, and slopes of the land, making them valuable for various activities such as hiking, mountaineering, and land development. Navigation. They are essential for safe and accurate navigation in areas with challenging topography. Hikers and climbers use these maps to plan routes and avoid steep or hazardous terrain. Disadvantages. Limited scale. The level of detail on a topographic map can vary based on its scale. Maps at a smaller scale may not provide the necessary level of detail for specific activities. Outdated information. As the landscape changes over time due to natural processes or human activity, topographic maps can become outdated. Keeping maps current can be a challenging and costly endeavor. Next is hatchers. Hatchers are a specific type of symbol used on topographic maps to represent the steepness of a terrain, particularly the slope and direction of hills and ridges. They consist of short parallel lines drawn on the map to indicate the inclination of the land's surface. Hatchers provide a visual representation of relief and help map readers understand the topography of an area. Hatchers were commonly used on older topographic maps before the widespread adoption of contour lines to represent elevation changes. Contour lines have largely replaced hatchers as the primary method of depicting topography due to their ability to provide more precise and quantifiable elevation information. However, hatchers can still be found on historical maps and are occasionally used for artistic or illustrative purposes. They were systematized in 1799 by Major Lehmann, an Austrian military officer, where line width became directly proportional to steepness. It hence became quite commensurable but not very imageable, blank on top and in valleys, and shortly after a northwest light source was introduced to enhance imageability. This was the main type of relief depiction throughout the 19th century. After accurately surveyed heights became available through the 20th century, hatchers gave way to contours, but they are still used for very steep slopes, such as cliffs, quarries, and railway cuts, where contour lines would merge. Advantage: Intuitive representation. Hatchers can be especially helpful in illustrating terrain for people who are not well versed in reading topographic maps. They offer an intuitive representation of the land's topography. A disadvantage is limited detail. Hatchers are less detailed and may not effectively represent subtle variations in the landscape. Contour lines and DEMs offer a finer level of detail. Next, we have our contours. Contours in a topographic map are lines that represent the elevation and shape of land surface. They connect points of equal elevation above a reference point, such as sea level. Contour lines are a fundamental component of topographic mapping and provide a clear and precise way to depict the topography of an area. Contours came initially from the need to know exact depths in water and were generated from a series of depths or soundings. The first contours in the late 1900s were on navigation charts as isobaths, since hatchers was not suitable for unseen landscape. Contour lines indicate the elevation of the land at various points across a specific area. By examining these lines, engineers can identify high points, peaks, low points, valleys, slopes, and other significant terrain features. Contours help in analyzing the steepness of slopes. Engineers can quickly assess the suitability of a site for construction, calculate cut and fill volumes for earthwork, and design roads, bridges, and drainage systems based on the terrain's characteristics. So, what are its advantages? It is the most commensurable quantitative method. It is also the origin of many newer depiction techniques, and it is now familiar to many users. For its disadvantages, it is an abstract method. There are no counterparts to lines on the ground. It is poorly suited to small scales. It is less imageable, but depending on contour interval, map scale, landscape type, and user's experience. Next topographic map is the hypsometric tints. Hypsometric tints in the context of topographic maps are a specific cartographic technique used to represent variations in elevation or terrain relief through the use of color shading or patterns. These tints provide a visual depiction of the elevation zones of a topographic map, helping map readers quickly grasp the spatial distribution of terrain heights. The addition of color to elevation levels was first tried as early as the 1830s. Color schemes require graduation, logical sequence, and realistic colors, with the darkest still able to bear readable text. Hypsometric tints divide the elevation range of the map area into zones, each represented by a different color or pattern. These zones may vary in size depending on the map scale and the desired level of detail. For its advantages: enhanced visualization. Hypsometric tints provide a quick and intuitive visual representation of elevation variations across a landscape, making it easier for map readers to understand the terrain's overall topography. Quick terrain assessment. They assist in rapidly identifying areas of higher or lower elevation, helping users assess potential water flow, drainage patterns, or the distribution of highlands and lowlands. For its disadvantages: lack of precision. Hypsometric tints do not provide precise elevation values. While they offer a sense of relative elevation, they don't offer exact numerical elevation information that contour lines provide. Legibility. Poor choices on color contrast, labeling, or colorblind unfriendly schemes can make hypsometric tints less legible, diminishing their effectiveness. Next, we have our shaded reliefs. A shaded relief combines contour lines and elevation data with stimulated lighting to create a three-dimensional effect that mimics the way terrain appears when illuminated by natural or artificial light. Shaded relief maps are designed to provide a visually appealing and intuitive representation of the Earth's surface, emphasizing the land's relief and the three-dimensional features. They combine elevation data with stimulated lighting to create a three-dimensional visual representation of terrain. Shaded reliefs maps enhance understanding of topography and are used for outdoor activities and educational purposes. They provide an intuitive, engaging, and visually appealing way to interpret the Earth's surface and its features. For its advantages, visual appeal. Shaded relief maps are visually engaging and provide an immediate sense of three-dimensional topography, making them more appealing and easier to interpret than traditional topographic maps. Intuitive understanding. They offer an intuitive way to understand the land's relief and spatial relationships of landforms, which is particularly valuable for outdoor enthusiasts, hikers, and mountaineers. Disadvantages. It is potentially misleading. The use of stimulated lighting and shading can sometimes give the impression of significant height differences where they might not exist, potentially leading to misunderstandings about the terrain. Subjective design. The choice of lighting angles and color schemes is somewhat subjective, and different map makers might create different shaded relief maps of the same area. This can lead to inconsistencies and confusion among map users. Next, we have relief contours. This technique of map This technique of applying a northwest light source to a contoured landscape was first tried in 1850, but printing methods then could not handle gray backgrounds to be able to highlight illuminated lines. This technique is also known as the relief contour method. It was pioneered from the 1950s by Kitoro Tanaka, who produced some exquisite examples using a theory of application of shading principles to contouring. The relief contour method is a technique used in topographic mapping to represent the three-dimensional relief or topography of an area on a two-dimensional map. This method is particularly useful for areas with complex or rugged terrain such as mountainous regions. Advantages: enhanced visualization. The relief contour method provides a visually engaging and intuitive representation of the land's three-dimensional features, making it easier to grasp the terrain's complexity and characteristics. Improved interpretation. The method emphasizes significant landforms such as ridges, valleys, and slopes, enhancing users' ability to interpret the landscape and plan routes or activities effectively. Disadvantages: limited precision. The relief contour method, like traditional contour maps, does not provide precise elevation values. It may be less suitable for applications requiring highly accurate elevation data, such as engineering or scientific research. Cluttered appearance. In areas with intricate terrain or densely packed information, the map can appear cluttered, making it challenging to read additional data such as roads, labels, or other features. Next topographic map are block diagrams. Block diagrams in topographic mapping are a specific type of graphical representation used to illustrate and analyze geological structures and the subsurface features of an area. These diagrams are primarily employed in the field of geology, structural geology, and the geological engineering to depict the arrangement and relationships of rock layers, faults, folds, and other geological elements. Block diagrams aim to represent the geological structures of an area in a three-dimensional format. This allows geologists and engineers to visualize the subsurface features and their spatial orientation. Block diagrams simplify complex geological structures by breaking them down into more manageable and understandable components. They provide a clear visual summary of the geology. Here are the advantages. Three-dimensional insight. These diagrams offer a three-dimensional view of geological formations, which help geologists and engineers to visualize the arrangement of rock layers, faults, folds, and other structural elements. Structural analysis. Block diagrams are instrumental in structural geology, helping professionals analyze the orientation and movement of rocks, fault systems, and folds which is essential for various applications, including resource exploration and civil engineering. Disadvantages: simplification. While block diagrams simplify complex geological structures, they do so by abstracting the subsurface features. This abstraction may lose some of its finer details and complexities present in actual geological settings. Limited data integration. Block diagrams typically do not integrate quantitative data, such as precise measurements of rock thickness or fault displacement. They are more qualitative in nature.
So now we're going to talk about contours. When we talk about contours, most of the time, the first thing that comes to our mind is makeup contouring. Well, they are not entirely that different because makeup contouring is emphasizing a feature on your face by drawing lines to accentuate that said feature. In surveying, contouring is emphasizing the elevation of a specific surface on the earth. So contours are imaginary lines that connect points of equal elevation. It is used to represent the shape and elevation of the terrain or land surface. There are different types of contours: index, intermediate, supplemental, depression, and approximate. An index contour are heavy lines thicker than the standard contour lines. Essentially, they are the indicators of elevation. They are normally shown every fifth contour. They carry the number of or elevation designation. Here is an example of index contours. Intermediate contours are lighter lines found between index contours. They comply to the interval rules of the index contour and they are usually unlabeled. For intermediate contours, there are times that there are going to be lines of close distances or either they merge into a single line. There is a technique called feathering that involves not portraying lines of close distances so that it could be read. So in the next slide, that is an example of an intermediate contours. And next is an example of feathering. As you can see, they do not portray the lines that have close distances so that it may be readable to others. Supplemental contours are used when the terrain is so flat and the intermediate contours are too far apart. They are drawn as dashed lines or lines of dots. So here is an example of supplemental contours. Depression contours are used to show low spots around which contours close. Peaks are drawn perpendicular to the contour lines on the downhill side. Sometimes these are called hatchers. So that is an example of a depression contour. Next are approximate contours. They are used when contours cannot be drawn accurately. It is the educated guess of the maker of the map. So this is used when the area that needs to be contoured cannot be physically surveyed. Let's now proceed to the contour interval. A contour interval is the vertical distance or elevation difference between two adjacent contour lines on a topographic map. Contour lines are used to represent the shape and elevation of a terrain in a specific area, and the contour interval is used to represent the shape and elevation of that area. Large intervals are used for areas with steep scale. Usually, the larger the scale, the smaller the interval, and the smaller the scale, the larger the interval. Since we have talked about the contour interval, let us now identify its selection. Selection of contour intervals. Relative costs. The cost of the map will be higher as the contour interval is reduced. Purpose of the map. It is important to balance the level of detail required for the intended use with practical considerations. Nature of the terrain. It directly influences the accuracy, readability, and usefulness of a topographic map. Scale of the map directly affects the level of detail and precision that can be achieved in a topographic map. The purpose of the map in topographic surveying is a critical factor in selecting the contour interval. The goal is to balance the level of detail required for intended use with practical considerations such as cost, readability, and the nature of the terrain. Understanding the nature of the terrain is essential for selecting appropriate contour intervals because it directly influences the accuracy, readability, and usefulness of a topographic map. By tailoring the contour interval to the terrain-specific features and characteristics, you can create a map that best serves its intended purpose. Lastly, the map scale directly affects the level of detail and precision that can be achieved in a topographic map. The scale determines the amount of terrain that can be represented on the map, and this in turn influences the choice of contour intervals. So here are the characteristics of contours. 1. All points on any one contour have the same elevation. 2. Every contour closes on itself either within or beyond the limits of the map. 3. A contour which closes within the limits of the map indicates either a summit or a depression. 4. Contours on the ground cannot cross one another except where an overhanging cliff, a vertical ledge, or wall is represented on the map. 5. Contours are evenly spaced on a uniform slope. 6. Contours are straight and parallel to each other on plane surface. 7. Irregular contours signify rough, rugged terrain. 8. The horizontal distance between adjacent contours indicates the steepness of the slope of the ground. 9. Contours cross curves in a crowned sloping street in a typical U-shaped curves. And 10. Contours cross streams in a V pattern pointing upward.
Locating contours, coordinate, squares, or grid method. Elevation, the corners of each grid can be obtained by differential leveling or trigonometric leveling. The contours are interpolated between the corner elevations by estimation or by calculated proportional distances. The drawback of this method is that no matter how dense the grid, critical points, high and low spots, and slope changes will not generally identify. As mentioned earlier, the most common method of representing the topography of an area is to use contour lines. A contour line is an imaginary level line that connects points of equal elevation. When using contouring, it is important to use map scales. A map scale is the ratio of the length of an object or feature on a map to the true length of the object or feature. Map scales are given in three ways. First, by ratio or representative fraction, such as 1 is to 500. Second, by an equivalence, for example, 1 inch is equal to 200 feet. Third, graphically using either a bar scale or labeled grid line spaced. On maps, contours represent the planimetric locations of the traces of level surfaces for different elevations. Rules of contouring. A contour line must never split or divide. A contour line must never simply and except at the edge of the map. A contour line must represent one and only one elevation. A contour line may never intersect other contour lines, except na ay overhanging cliffs. There are several rules to note when viewing topographic maps. The first is the rule of V's. This indicates that sharp pointed V shows a extreme valleys. Second is the rule of O's. This indicates that closed loops are normally uphill on the inside and downhill on the outside, and the innermost loop is the highest area. Lastly is the spacing of contours. Closed contours indicate a steep slope while widely distant, widely spaced lines displays a shallow slope. So checkerboard method. In constructing contours, there are three steps. First step is developing a contour map, is measuring the elevations of a group of points. The second will be it will be easier for us to establish
elevations of the said group of points if we used flags. Third, the location of the flag points can be established by taping and checked by pacing or the odometer. So this is the start of the checkerboard method. Once your contour grid is established, measure the elevation of each grid point. So every cell, there are 4 grid points. We have to measure the elevation of each points. For this example, we want a contour map with 5 feet intervals. The grid is rectangular. The dimensions of the sides are 80 feet north and 100 feet east. So the longest side, which is the length, measures 100 feet while the width measures 80 feet. The basic method for estimating contour is applied to each grid individually. We use linear interpolation to find the location of the desired contour interval, which is 5 feet. Let's consider the cell in the upper left and remember the contour interval is 5 feet. So, mao ni. First, first, see if a contour interval exists between the nodes of the grid cell. So, the nodes are the points corners of each cell. If so, estimate where along the side the contour interval would be located. So if there is a contour interval present between sa node sa edge sa cell, we use simple linear interpolation to each side to locate the contour interval. So starting from the top edge of the grid cell, which is kaning nasa taas, nga naay dimensions nga nagta-start sa 98 to 102, we know na 5 feet ang contour interval. So between 98 and 102, there na ay value nga divisible by 5 which is 100. So mao na atong contour nga point. So to measure the location na nga point kay we could find its slope. So ang slope kay ratio in proportion lang. The 102 minus 98 over 100. Ang 100 kay ang length sa sa rectangle which is 100 feet nga east. And then ang B-intercept is 98 kanang first point. And in order to find the distance from the B-intercept to the contour point, we use kanang formula sa lower left. So 2, ang kanang 2 kay 100 minus 98 na. So 2 times 100 over 4. Ang 4 kay gikan na sa difference sa mga dimensions sa taas which is 102 and 98. So muna na ang distance sa contour point from the B-intercept. So from 98, ang kanang 100 kay 50 feet na siya from 98. So next kay bottom edge of the grid cell. So ang sa bottom edge sa grid cell kay 101 o 108 ang points. So in order to find the slope, we use ratio proportion. 108 kaning second nga point minus 101 which is kaning first point sa lower left over 100 which is the length of the rectangle 100 feet. And the B-intercept is the lower left nga point which is 101. So para sa gaina, in order to find the distance from the B-intercept, we use kaning nga formula. Kaning i-subtract ang 105 from 101 which is 4. Yang 100 which is the length sa rectangle. And then over 7, yung kanang 7 kay difference na sa kaning second point ug first point which is 108 o 101. So with that formula, we were able to solve the x value. So 57 feet. So pasabot ang 57 feet kay ang 105 gikan sa 101, 57 feet lang distance. So next kay left edge na pod sa grid cell. So ang left edge kay kaning mag-start sa 98 paubos nya ang ubos nga point kay 101. So between ana nga points kay ang value ra nga divisible by 5 kay 100 lang. So muna atong point contour point. In order so repeat ra gyapon ang process sa pag-find sa slope sa kuan gyapon ratio and proportion ang B-intercept kay 98 gyapon. And then finding x kay na we subtract 100 from 98. So we get 2. And then Ang width sa rectangle kay 80 feet man, so muna atong i-multiply sa difference atong unang kuan compute unya i-divide nato sa difference sa second point ug sa first point, which is 101 minus 98, so munang 3. So with that, we were able to get 53 feet. So ang distance from the B intercept nga 98 to the 100 kay 53 feet. So sa kaning sa last, mao ra gyapon ang process, same na gid sila. And then after doing everything na, we can connect na dayon ang points nga similar elevations. So kaning 100, i-connect nimo siya sa points nga 100 po ang value, niyang 105 po ang value. So if we simply connect points of equal contour intervals, ang ma-show sa right kay ang kuan na ang tanan nga kuan, tanan nga points na connected kani nga 3 by 3 nga grid cell. So muna ang itsura sa contour maps using checkerboard method. Thanks for watching.